So let's state and prove the following important proposition about product groups. So we'll let G be a group, and then we'll let H and K, those will be subgroups of G. And then we'll define a map, a function, H cross K to G, but we aren't going to know if this is a morphism just quite yet, but what it will be is it'll just be the multiplication map. HK goes to H times K. So that's just the multiplication map, and then we can see that the image of F is the set HK under this sort of product of sets notation, right? Which is the set of elements little h, little k for little h and big H, little k and big K. Meaning that, it's just the set of all things that look like a product of the thing in H times times the thing in K. So this is just a comment, I guess, that we can see from the definition. Now, what the proposition actually says is there's 4 parts. Yeah, this is a little bit of a behemoth, but it's also very important. So F is injective. If and only if H intersect K is E, the subgroup which is exactly the identity. The second part says that F is a morphism if and only if, oops, my M is a little bit out of place, if and only if so I guess the way we would say this is elements of H commute with elements of K. And so what that will mean precisely is the following, right? It's for all H, K, H being in H and K being in big K, HK will be equal to KH. So maybe I'll erase this because I want to write there later, but the idea, right, is that when you have a product group like this product, elements from one side and elements from the other side have to commute. And it's going to turn out that'll be an if and only if. And that'll tell us if this multiplication map is going to be a morphism or not. Okay, the third part is let's see. If H is a normal subgroup, G, then HK, the image, is a subgroup. So remember, it's not always true that the product set of 2 subgroups is itself a subgroup. For example, you can take S3 and you can take the subgroup generated by one reflection and the subgroup generated by a different reflection, and the product, will have 4 elements in it, and there's no subgroup of S3 which has 6 elements. So a subgroup of S3 can't have 4 elements by the counting formula, say. So this can't always happen. But if H is a normal subgroup, it does. And finally, maybe the most important one, putting it all together, is that F is an isomorphism if and only if. And then we have to have a couple of things. We have to have, number one, part A holds, right? H intersect K equals the identity. Number two, we have to have that HK, well, this isn't part B. What it is we have to have that H times K is the entire set G. And third, both H and K are normal subgroups. So if all 3 of these things happen, this happens, and this happens, then we have an isomorphism, and that's an if and only if. So if any one of them fails, we don't have an isomorphism.